Okay. Good afternoon to everyone. Myself Akash Sharma, and on behalf of MIDAS IT, I welcome you all to this webinar in which basically I will be introducing you to the rock and seepage module of SoilWorks. So first of all, we'll start with the seepage module. Basically, I would be covering most of the seepage module part where demonstration, focusing on two types of analysis which we could perform, that is the steady state analysis and the transient state analysis. As you know, whenever we are constructing a dam, or whether it be earth dam or any canal supporting structure, the thing happens is that the water level is not constant throughout. At the beginning, the water level changes, and to consider that, you can perform the transient state analysis available with SoilWorks and also the steady state analysis. Also today I will be showing you the effectiveness or the importance of the coupled analysis. Coupled analysis, basically what happens is that we extract the pore water pressure variation after concluding the seepage analysis, and then we use that pore water pressure to analyze the stability of the dam. It will be better demonstrated, so I'll just start with the demonstration part. Okay, so this is basically the interface of MIDAS SoilWorks. So any module you want to work with, just click on that particular module. So we have the ground module, the slope module, the rock module, the soft ground module, foundation, seepage and dynamics. So I'll just click on seepage module. Okay, so initially you need to define the initial parameters, which is basically the unit system you want to work with. So you can select SI, CGS, FPS, or you can use the user defined unit settings. So just click OK and click OK. Now let me import AutoCAD file. I'll just import an AutoCAD file. Sorry. So just go to the SoilWorks icon, import and CAD file, and you can select the AutoCAD file where you have just kept it. So I'll just open it. So open. So this is basically today's problem we are going to solve. Actually, we have an already existing leaf and we have the rest of the parameters, rest of the soil profile, and we want to create an extra embankment with it, and would be considering a riprap to take care of the seepage analysis. So just to save time, what I will do is that I will import the already defined file. So once you have you have created the material properties for any model, what you can do is that you can just import it directly from the database. So just go to SoilWorks icon, import database from another file, and just select the file, the folder in which you have saved. So please take care that you just need to select the folder where you have kept it. So introduction, and just click OK, import data. So now let us see the material properties which we need to define to consider the properties. So go to model, ground material property, landfill layer. So the property which you need to define are the horizontal permeability coefficient, the vertical permeability coefficient, and the rest of the parameters. So I will just a second, let me import once again the properties. I'll just actually the same properties has been imported, so I'll just import it once again. Okay, import data. So these are the parameters which you need to define. So the horizontal permeability coefficient, the vertical permeability coefficient, and also like since we are going to consider the unsaturated property of soil, that is, we have two kind of analysis. One is the steady state analysis, in which the water level is constant, so you need not go for the unsaturated properties. But what happens is that when the water level changes, the permeability changes with the change in the water content and porosity. So there are different function type which are available with SoilWorks like Gardner, Frontal, Van, and also you can define your own user-defined permeability pressure load, or what we call the water content pressure variation, to consider the unsaturated property of the soil as a result of the transient nature of analysis. So this you can consider in SoilWorks. So having defined, now let me show you the easy workflow which we adopt with SoilWorks. So first of all, to assign the soil properties, we need to create the surfaces. That is, the soil properties can be assigned only to surfaces. So geometry, smart surface. Now to assign any property, just select that surface, drag and drop the property. So the bottommost layer being the weathered rock, then the weathered soil, then the alluvial layer, and this is my existing leaf. And now I want to create an embankment over my existing leaf, and thus want to check the seepage analysis. And finally the riprap. Okay, now having defined the properties, next thing we need to do is meshing. So go to model, go to smart mesh, select very fine mesh and click OK. The program automatically creates the most optimal mesh generation. You can see with the coarser mesh at the bottom and with the finer mesh at the top. Now the next thing which we need to define is the nodal head conditions. So just go to boundaries, the nodal head. So let the name being the left hand static. With the static, I mean that the nodal head is not changing with time. Since we are going to do transient stage analysis, we need to consider one head set in which basically the water set is varying with time. So with left hand static, I means that it is static. So let the object type be curve, select the curves, and let the nodal head value be in 18.42 and just click apply. Now let us define the variable head for the same. So let the name being left hand variable head and select the curves. Now here you have to input the nodal head value as 1, and in the function type you can define the function in which your water level is going to change. For example, as you can see that first the time is in seconds. So first 0, from at the starting it was 15 meter, but with time it get higher to 18.42, and finally when it stabilized it was 15 meter. So this is basically how my water level is changing. So you can now use that function to define the boundary water level. So just click OK. Now the next thing which we need to define is the review boundary. Review boundary is basically nothing but you need to define the boundary condition on the downstream sides, so the program can iteratively go on processing for these curves and thus get you the results. What I mean is that in the review boundary, basically you need to say, or you need to just assign the program the curves with which you want or expecting the flow to occur. So let the name being nodal flux, that is out of which the water is expected to coming out after seepage. Just change it to curve, select the curves, and click OK. So it is as simple as that. Now you need not, you have just completed the model, and now you need to generate the analysis case. Go to boundary and analysis case, click add. Now the first case, as I was discussing, was the seepage state analysis or the steady state analysis. So let the name being steady state. Use all mesh sets. In the boundary sets, we need not use the left hand variable head because this is for the transient state analysis. So in the analysis control, basically you can control the maximum number of iteration. So let it be the same. Click OK, click apply. So it is created. Now next is the transient state analysis. So make it transient state. Now in the transient state, once again drag and drop the left hand variable head in the data to be used in the analysis. And in the analysis control data, you need to define the time steps. Time steps are basically the steps where the program will calculate the value and give you in the results. So this should basically be the point where your water level is changing. So as we defined it for the same, we will create the time step. So let the value being 259200 and in 4 steps. So this is the same value for which you have defined the water level function. I will just show you. So create steps and let the value be 172800. So if you want any at different time steps or at different time location, you can just create the location. For this particular case, I am calculating only at that point where there is a change in the water level. So click OK and click OK. Now you can just run the analysis, perform analysis. You can just save it. So you can just perform the analysis. Now just to save time, I have already analyzed a file and I will just show you the results. So let us start with the steady flow analysis. So in the steady flow analysis, you get the vertical hydraulic gradient, the horizontal hydraulic gradient, as well as you can get the total head variation in the embankment, the pore pressure head variation, similarly the pore pressure variation, and phreatic line. Phreatic line is basically the top line of flow. And also if you want to know the flow quantity or the flow path, so you can go to results. In the flow path, you just click on any point and you can see that how it is going to flow. What are the basically the seepage flow lines. Also if you want to know the exact value, you can go to results, flux results, and basically you can just click on any particular node and calculation. So it will give you the amount of water coming out of that point. So in this case it is 0. So once again calculation. So you can see that 6.9 meter cube per second per meter. So that is also possible. So these are basically the various results which you get. Now in the transient state analysis, basically you can see that how the phreatic line changes with time. So for example, initially when the water level was 15 meter, you can see the phreatic line was below, and with time when the water level raised to 18.2, how the phreatic line changed, and finally at the final stage how the phreatic line changed. So this is how you can perform the transient state analysis and proceed on. So now the next thing which is very much important and very much effective is the coupled analysis. Now to show you in detail, what I will do is that I will just open a slope module, and as Mr. Subham has already demonstrated a slope module, I think you are pretty much familiar with the workflow which we adopt in slope module. So I'll just create a simple, the thing is that I will create the same model. I will just import the same CAD file. Okay, but now since I'm going to perform a slope stability analysis, so I will define a limit equilibrium property. So in the database, I'll just select limit equilibrium properties, and I'm just assigning a few layers for my model. So just for demonstration part, I'm using few of the layers. So let's suppose now we'll just create the surface and we'll just assign the properties. Now having assigned the properties, the next thing we'll do is we'll just import the results from already existing file. I will just show you how. That you go to limit equilibrium method, and first of all we'll need to create the boundary surface. So just we'll be considering the left hand stability. Left hand stability means what is the stability for the left hand side of our embankment. So I'll just draw the grid range for the assumed center of rotation, and let the number of increments be 10 and click OK. So what basically I want to show you is that when we let us perform a simple LEM analysis on this model. So let the name being LEM, we'll be using all layer set, boundary sets and load sets, and in the analysis control data we'll just make it right to left the failure. Close, and I will just analyze it. So this is my embankment where I have not considered any pore water pressure variation. Now you can see that the factor of safety which we are obtaining is something 2.1816. Now I want to show you that after the seepage analysis, we found that there was some pore water pressure variation in the model. Now I want to consider the pore water pressure variation in my analysis, in the limit equilibrium analysis, or let's say in the strength reduction method analysis, so that how it influences my slope stability could be checked. So what you can do is that you can just unlock it. You can go to the loads and boundaries, and here there is an option called result from other case. So just click on that. You need to select the model, and please take care that the model is the one which you have performed the seepage analysis. So seepage, so just make it seepage module because the module was created in seepage model. So you need to change this and just click open. So you can see that all the pore pressure variation for the 5 analysis, that is the steady state analysis and the 4 transient state analysis, have been imported. Now you can select any of the pore pressure variation and say import results and just close it. Now you can find that in the load you have this result, that is the stability check for a river leaf, and this is the transient state analysis for the first stage, that is time when it is 64,800 seconds. Now I will consider the same in my analysis case. So analysis case. So let us modify it. Now just drag and drop the pore water pressure result which we have imported, click OK and close it. So analysis, perform analysis. Now you can see that the factor of safety has reduced considerably, let's say by amount of like something 0.8. So you can see that how important is that to consider the pore water pressure variation in slope stability analysis. Now to check, you can see like this is my phreatic line for the initial state and this is my failure surface. Now if you click on any particular slice, you can even see the pore pressure value which is being taken into calculation for the slope stability calculation. So thus you can consider the seepage analysis for your model, as well as you can consider the coupled analysis using the slope stability module and importing the pore water pressure variation from the seepage module. So moving back to the presentation. Next, I'll talk about the rock module. Now in the rock module, the analysis capabilities we have is that you can perform the stereographic analysis as well as you can perform the LEM analysis for the various kind of failures. Now what are basically the different types of failure? First of all, to start with, why we need rock module when we have the slope module for the analysis? If the rock variation, like it is for weathered rock with soil and all, and the failure could be well defined by arc failure, then you can use the slope module for the slope factor calculation. But the types of failure which actually happens in the rock are different. As you can see on your screen, they are like plane failure, wedge failure and toppling failure. Now this couldn't be considered in the arc failure, where arc failure LEM method, where basically we consider the failure to be a circular and hence the plane and wedge and toppling kind of failure couldn't be considered in the slope module of SoilWorks. Also, I would like to highlight that you can consider the weathered rock properties in slope module also, considering the arc failure conditions. So now to consider the various types of plane failure, first of all let us talk about the plane failure. It basically occurs when the dip of slope is greater than that of the discontinuity surfaces, and since it is a case of the plane strain elements, 2D analysis is performed. Now the assumption which we make are that the strike of slip surface and the tension crack is identical to that of the slope, and hence you can perform the 2D analysis, and both side faces of the failure block are relaxation faces and no resistant force acts on them. So it is basically a plane strain problem and hence could be solved. Now next we have the wedge failure. Now it occurs when the discontinuity surfaces in two directions intersect. So now the geometry shape and the forces should be considered, and hence 3D analysis becomes very must, and you can't go for 2D analysis. Now the conditions where the wedge failure occurs in rocks are: first, the failure occurs when the driving force that slides down is greater than the shear strength of the joint plane, and the second is that the plunge of intersection of two discontinuous surfaces should be smaller than the dip of slope. Now, how do we perform the stability analysis? It's very simple. The factor of safety is calculated as the resisting force upon the driving force. Now, the resisting force, as very much clear from the figure, is the shear strength or the shear resistance provided by the failure plane. So it depends on tau into the length of the failure, and the driving force is basically the horizontal component of the weight or the self weight, that is W sine theta. So the factor of safety becomes very much simple to calculate. Now the advantages with the slope or the rock module is that it considers the basic steps. It considers the variation in slope shape and various bench shapes, the variety of loads like static, seismic load, water pressure, and external load could also be considered, and their influence could be studied, and various reinforcement like rock bolt and rock anchor could also be considered to check the stability for the rock. Now, talking about the soil material definition, the most important factor in calculating the factor of safety of rock slope are the exact simulation of the scale of failure block and definition of shear strength of joint plane. So basically the shear strength is the parameter, as you have seen in the previous slide, which governs the factor of safety. Now the various models which are available with SoilWorks are the Moore column, that is basically on the simple formula where the shear strength is given by sigma and 10 phi plus C, where C is basically the cohesion, phi the friction angle, and sigma n is the normal stress. SoilWorks also provides with Barton-Bendis where the tau is calculated as per the formula which you can see on the screen, where JRC is the roughness coefficient of the contact is also considered, and the compressive strength of contact is also considered using the parameter JCS. SoilWorks also provides with the Hogg-Brown model and the generalized Hogg-Brown model, and also there's a special option of power curve where you could consider the shear strength as per the variation in the normal stress, with A and B being some constants where you need to define as per the property of the contact layer. Now it is very difficult to accurately define the mechanical behavior of the rock joint plane with one material model. So rock module also provides with options of roughness and filling materials. Like as you can see in the roughness of joint plane increases, the shear strength increases, and the factor of safety also increases. So you can consider the shear strength as per formula sigma n 10 phi r, where tau r is basically the shear strength of the roughness between the two sliding surface, and phi r is the friction angle of the roughness. Now most of the filling materials which are found in the joints are sand, silt, and clay, which reduce the shear strength of joint plane. Now the thickness and the strength characteristic of the filling material decide the stability of rock slope. When the filling materials are taken into account, the shear strength of the joint plate is defined as formula shown on your screen. So where mu is basically the ratio of the shear strength to the normal stress. So you can consider the roughness and filling materials and hence could effectively simulate the contact between the two. Water pressure. Whenever we are dealing with rocks, the most important thing which becomes to consider is the water pressure and its variation basically in the joint planes. So first is the linear distribution. Linear distribution basically we take into account when the water which peeps in comes out, which doesn't comes out at the bottom level. So the water goes on accumulating and hence we can consider a linear distribution. But when the system, when it changes that the water comes in the plane and comes out simultaneously, we go for a triangular kind of distribution. Also, like if you know the exact water pressure variation in the ground condition, you can go for uniform distribution or user defined, where basically you don't give any like unit weight of water. You directly can define it as a uniform pressure load and consider the load as a uniformly distributed load, directly inputting the value. Now the tension crack criteria, many a times you can go for a simulation where basically the lower part of the joint doesn't have any water, so tension crack criteria could be used to simulate that particular kind of variation of water pressure. Also, you can perform the static seismic analysis. Now, static seismic load refers to the static load converted from the dynamic load that occurs. So, the failure block weight is basically multiplied by 50% of the maximum horizontal ground acceleration of seismic wave and is converted to an equivalent static load, and then the stability is checked. Now, if the maximum horizontal ground acceleration due to seismic load is, let's say, A max, the lateral load that is additionally applied to the failure block is calculated as shown below. That is KH is equal to A max G and 50% of the weight. Now let me show you how one work with the rock module. So I'll just open a new file. So let me just close this projects and I'll just open SoilWorks. So to start with, you can select rock. Now having selected the rock, the next thing we'll start with, we'll just open a new project and let the name be new project and click OK. Now the job selection, so we are going for the stability of the slopes. Okay, now to start with, first of all you need to define the slope. Now we have two kinds of failure, plane failure and the wedge failure. Now first of all let me take the plane failure. Now you just need to define the unit weight, the upper slope. Just to show what the upper slope and the various parameters which we are defining, you can just click on this icon and you can see what are the various parameters. So the input method, let it be angle, where you just want to define the angle. The h value, that is the initial height, let it be the 15 meter, the width being 12.6, the angle being 50, and the rest of the parameters let it be same. So just click OK. So this is basically my slope variation which I'm going to consider. So if you want to just consider single slope, you could have chosen 0 for the rest of the slope parameters. Now, next important thing is joint. Now, for joint, first you need to define the angle, the tension crack parameters, that is its angle, its length, and the properties with which you are going to define its parameters, like Moore column, Branton-Bandis, Hogg-Brown, generalized Hogg-Brown or power curve, the detail of which I have shown you in the presentation. So just enter the cohesion and friction value. And also if you want to consider the filling and the roughness, you can consider the same. So let us just first start with the Moore column only, and then I will show you how much the roughness and filling could affect your factor of safety. So just click OK. So this is how the joint for the rock module has been created. Now you can see that as soon as you create it, you can check that what is the minimum factor of safety for this particular model without considering any water load, static seismic load, or any kind of reinforcement. So let us first check with the water pressure. So as I already discussed in the presentation, in the water pressure, you need to define the distribution type, which depends on the type of simulation that is occurring in real ground. That is linear, when the water comes in the joint plane and is not able to come out from the bottom. Similarly, we have triangle, uniform, and tension crack. So let us go for linear. The water unit weight remain as 1 ton per meter cube, and the percentage fill, let us consider it to be 100, and just click OK. So actually you can see that as soon as I have applied, now next I will consider the static seismic load. Now in the horizontal direction, you can just define the seismic coefficient as per the criticality of the area. Let it be 0.1 and click OK. Now let us check it for the reinforcement. So go to reinforcement property, and you have two types of structural property. One is rock bolt and the second is the rock anchor. So the tensile force 20. Similarly, you can give the pull out force and shear force if you want to consider. So just click add. Now having added, now let us apply it to the structure. So reinforcement arrangement, I'm considering the one I have created. Let the grouted length be, let's say, 10 meter. In the normal direction, my reference point, let it be 8. The vertical spacing being 4 and the horizontal spacing being 4. Just click add. So you can see that this is my arrangement. Similarly, you can increase it for different layers and you can directly go on adding. Okay, now if you want to consider the properties in the filling and the roughness, you can just click OK, and I'll just delete the water pressure for now, and now you can see that what is the factor of safety for your particular model. It's coming as 1.051 when I'm not considering the water, but as soon as I'm considering the water, say let's say just I will reduce the percentage fill, let's say 80, and it to be linear, and you can see that it is reducing by almost 1, that is 0.154, and thus one can understand the importance of the considering water in the analysis. Similarly, if you delete the seismic now, so just delete the seismic, you can see that the effect is very much less. It is something like 0.219 with the seismic coefficient which we used as 0.1. So thus you can consider the factor of safety and can check whether your arrangement is suitable or not. Now similarly in the same model I will just show you how we go for wedge failure. Wedge failure also you need to define various shapes. Now to understand the various parameters you can use the figure. Just click OK. Okay. Next thing you need to define the joint. So in the joint you need to define the how the joint plane 1 and joint plane 2 are varying, and similarly what are the various properties you are considering for the same, like property 1. So you can go for different kind of model, the filling and roughness could be considered, and just click OK. So this is basically my model. Now the factor of safety which we have obtained is 1.611. So let us define the water pressure. Let it be uniform and just click OK. So you can see the factor of safety has reduced to as 0.543. Now let us reinforce it. Let us go for rock anchor now and just click add. Okay. Now reinforcement arrangement. So this is a grid type of arrangement since we are going for a 3D modeling. So you should take care what is the reinforcement you are providing. So you can see that these are the various location and as programmed. Now as per this we can say as per this coordinate system where the coordinate 1 is at -3 and z is 0, coordinate 2 1925, and we are considering the horizontal division as 3 and 4. So if you make it finer, let's say 5 and 5, so you can see that the number of location where you can input is increasing. So let us increase it to 10, 10. Okay. So now you can use the two of the properties which you have assigned. Any of the properties you can just select and click add. So you can see that as soon as you add, the factor of safety has increased to 1.058. So thus you can consider the various kind of analysis in rock module of slope stability. So thus you can check whether a particular arrangement is suitable or not, how the seismic load or the water pressure is affecting your model, and simulate your reinforcement arrange at the same time and come up with the most suitable arrangement for the rock bolts or the rock grids. So with this, I thank you all for attending this webinar. Hope you find it useful. If you have any query, you can write us at techsupport@midasit.com. So once again, I would like to say you that if you have any queries, you can write us at techsupport@midasit.com. Once again, thank you all for joining this webinar. Thank you.